Ferrers or Young diagram is a graphic representation of a partition of a natural numbers. For example, 5 is 3 plus 2, and you can represent the 3 as a row of 3 squares here, followed by a row of 2 squares below it, which corresponds to the number 2. Now, this diagram, these squares can be also represented by dots. So the same partition can be represented here by 3 dots on the first row and 2 dots on the second row. Similarly, you have an example of 7. One of the partitions of 7 is 4 plus 2 plus 1, and you write these numbers in decreasing order, and then you have 4 on the first row, 2 on the second row, and 1 on the last row. Similarly, 3 plus 3 plus 1 plus 1 is a partition of 8, and you have the diagram over here. Now, if we rotate these diagrams, each of these diagrams, we get another Young diagram of the same number, and this is called the conjugate. So if we call the diagram on the left lambda, then we can associate to it a conjugate, and the rows of the diagram lambda become columns for lambda star, and vice versa. So the conjugate of the partition 3 plus 2 is just the partition 2 to 1 that you see here on the right hand side, and similarly, the conjugate of the partition 4 to 1 is the partition 3 to 1 1, and so on. So the conjugate of 3 3 1 1 is the partition 4 to 2. Now, from this simple observation, we can deduce a proposition, which is that the number of partitions of n into k parts is the same as the number of partitions of n in which the largest part has size k. And the proof is simply the fact that this correspondence going from one partition lambda associating to it its conjugate, this is a bijection between the two sets of partitions. Basically, if you have, for example, here we have, let's say k is 4, we have a partition into 4 parts, and to it we associate uniquely a partition of the same number 8, in which the largest part has also size 4, and so on. So it's just a neat observation, which leads to a very nice result. Now, let me give you another application of these diagrams to a problem in, I guess, combinatorics and number theory. Last time we talked about Pn, which is the partition number of n, the number of partitions of n. Now let's look at some related number. So let's define Pen as the number of partitions of n into an even number of distinct parts. So I'll give some examples in just a second. And similarly, we can define Pon as the number of partitions of n into an odd number of distinct parts. So I wrote here some of these numbers for some small values. I'll leave them to you to figure out. But let's just explain the entry here of 5. So 5, we want to write it in a sum, as a sum of an even number of terms, and these terms have to be distinct. So the smallest number of terms that you can have is 2, and we can write in that case 5 as being 4 plus 1, which are distinct, and you can write it also as 3 plus 2. And those are the only ways that you can write 5 as a sum of 2 distinct numbers, natural numbers. And then you can try to write 5 as a sum of 4 terms, but in that case, some of those terms are going to be 1. They're going to be equal, so that this is the only way, these are the only partitions that are counted by P of n. Now for the other part, where you write 5 as a number of, as a sum of an odd number of terms, each of them, all of them distinct, you can write 5 as 5 by itself, and that has one term, so that works. And then you can try to write 5 as a sum of 3 terms, but you can observe that no matter how you do it, 2 of those terms are going to be equal. You can do 2, 2, 1 or 3, 1, 1. So in that case, this number is 1. And similarly, you can try to calculate some of, I leave you to calculate other numbers here on this list. You see at 1, we have a bit of a discrepancy. We have another one at 5. Let's try some other number. Let's see how much could be, for example, P E of 9. So how do you write 9 as a sum of even number of terms? So you can write it as 8 plus 1, 7 plus 2, 6 plus 3, and 5 plus 4. If you try to write it as a sum of 4 terms, 2 of them will be equal. So this gives us 4. And then we can, if we want to write 9 as a sum of an odd number of terms, so of course you always have 9 is 9. So one term gets counted there. And then we look at for a sum with 3 terms. So we can have 6 plus 2 plus 1, 5 plus 3 plus 1, and 4 plus 3 plus 2. So it's also 4. Okay. So, okay, what's going on here? So before I state the result, which is a quite famous result of Euler, let me give one more definition, and I'm going to introduce what are called pentagonal numbers. So I will define omega of m as being 3m squared minus m plus 2, 3m squared minus m divided by 2 for m as a natural number. And what is this number? What does it count? Well, it's a sum of an arithmetic progression. So I'll draw it here. When m equals 1, we count just one dot. So, and you can see that in that case, if you plug in m equals 1 in here, you get 3 minus 1 divided by 2. So it's 1. Then the next one, you draw a pentagon here. So the next pentagonal number is 1 plus 4, which is 5. And that's what you get if you plug in m equals 2. You get 12 minus 2 divided by 2. And then you continue like that. So let me draw it here. You have a small pentagon and you put another pentagon around it. So we'll have this pentagon, and then we added this other pentagon around it. So in that case, we had 1 plus 4 from before, and we add another 7, and we get 12, and so on. The next one after this will be 1 plus 4 plus 7 plus 10, which is 22, and so on. So I'll just write the definition again on the next page. So for m natural number, I can define omega m as being this pentagonal number, which is 3m squared minus m divided by 2. And I can define, this is again the sum of this geometric of a arithmetic series, and we can also define omega of minus m as being what we get on the top if we replace m by minus m is 3m squared plus m over 2. Okay, so these are just two definitions of this pentagonal number. Okay. So now, what did So what did Euler prove? So here's his result. So Euler proved that for any natural number n, these two numbers are the same. So P E of n equals P O of n, unless n equals this one of these pentagonal numbers, omega of m, or n equals omega of minus m, in which case these two numbers differ by 1. So Pe of n minus P of n equals minus 1 to the power m. Okay, so for most values of the natural number n, the number of partitions of n into an even number of distinct parts is the same as the number of partition of n into an odd number of distinct parts. Okay, so let's just give a proof of a sketch of a proof of this result, because it involves, there is a proof, a bijective proof, which involves this notion of a Ferrers or Young diagram. Okay, so for that I need to define a certain invariants are associated to a Ferrers diagram. So let's start with defining these things by an example. So we had before, let's see some of these partitions. Okay, let's see. We have one of these partition of 9. Let's look at the partition in which is 5 and 4. So for the partition, let's write it 5, 4. We have the diagram here, and we define two things. The row at the bottom of the diagram, we call it base, and it's the length of the base, we denote it by b. So in this case, b is, in this specific case, b equals 4. Okay. And now we define another object. We look at the most, the rightmost entry and the topmost entry in the diagram, and we go down on at the 45 degrees angle going this direction, and we look at the segment that we consisting of the points of our diagram, the longest segment that we can it has to be continuous segment that we can find. So in this case, we can just go in just these two points. That segment contains these points, and we call this segment here, we call it the slope, and S is the number of points of the slope. So in this particular case, S equals 2. Okay, so let's just do a few more examples, and then we will sketch the proof. Let's take another partition. Let's take the partition maybe 6, 3. Okay, so in this case, the base is here, so b equals 3, and the slope is just 1 point. So in that case, S equals 1. Okay. Let's just do one more partition. Just do 4, 3, 1. So this is a 9. So 9 has a partition into 6, 3. 4, 3, 1 is a partition of 8. Let's write it this way. So we have 4, we have 3, and we have a 1 here. So in this case, the base is here. So we have b equals 1. And in this case, the slope is here. So s equals 2. Okay. So now, the procedure for proving this result of Euler is to actually construct a bijection between the sets of partitions of n into an even number of unequal terms and the set of partitions of n into a odd term of unequal parts. So you can start with one partition of one kind, and then we can proceed. I'll show you the construction that constructs a partition of the other kind. Okay, so let's tidy up here. Let's start, for example, with this partition of this kind. Let's start with one that is counted by PE of n. So it could be something like the partition here on the top. You have a partition that has has two parts into has two parts, and those parts are different from each other. Just a second. Okay, and when we have such partition, so let's say we have such a partition. Let's okay. Okay, let's say we have such a partition here. So in this, you take such a partition and you look at the length of the base, this b here, and you look at the length of the slope. So this is we have the b here, and we have the s here, and we have two possible cases. So case one is when b is less than or equal to s, which is the case in the figure here. So in that case, what we do is we remove the base and we adjoin it to the diagram to form a slope parallel to the current one. Unless, so we do that all the time, unless there's one case when we don't do that, unless b equals s, I'll deal with this in a second, and base and slope intersect. So their intersection, there is a point. But for us, in this picture here, on the left, we have the case in which the base has so our base here, B, has size 1 and S has size 2. So what it says is you take this base from here, from the bottom, and you move it to the top. So the partition that we have here in blue, that's a partition, what is it? On the first row, we have a 6, then we have a 5, then we have a 2, then we have a 1. So it's a partition into an even number of terms. And that changes to, we move the 1 from here and it goes over here. And what does that become? That becomes the 7, 5, and 2. So it's a partition into an odd number of terms that that adds up to the same number. Okay. So this is in this case where the base is less than or equal to s. Modulo this case here, when b equals s and the base and the slope intersect. And what happens there? Well, that situation we are here. We have this picture. We have, say, something like 5, 4, and 3, and in this case, the base is here, b equals 3, and the slope is here, s equals 3, and in this case, n has a special form. It's actually, you see it, it's a sum of consecutive numbers. It's going to be b plus b plus 1, and one can work it out that the term at the top is 2b minus 1. And when you expand, when you calculate this is exactly omega of b. So in that case, we do not do this this procedure. So if that was the case, so in this situation, you have a partition into an odd number of terms. So this one doesn't have a match in a partition into an even number of terms in this situation. Okay, so that only happens if n has this special form. Now, so case 1 deals with b less or equal to s. Case 2 deals with b greater than s. So let's do a picture here of b greater than s. So let's take, so in this situation, b is here, b is 4, and s is here, s is 2, so b is greater than s. In this case, what we do is we remove the slope and we put it at the bottom of the diagram. So remove the slope and join it to the bottom of the diagram. And here there's an exceptional case, unless b equals s plus 1 and the base and the slope intersect. So I'll deal with the exceptional case in a second, but here, when you have b strictly bigger than s, and we are not in this exceptional case, like in the picture over there, we have the partition on the top, it's a 5 and 4, and how does that change? So we shave a 1 from both of these parts, and we put it here at the bottom, and this diagram is now this one is not here anymore. This diagram is 4, 3, 2, and you see again, you change the number of terms in the partition changes parity, and actually all the terms are distinct. Now, what's the situation with this exceptional case when b is s plus 1 and the base and slope differ by 1? It's quite similar in some sense to the previous case. So let me give you an example here. You can have something like this. So in this case, you have the partition 6, 5, 4. And if you look at the bottom, you have the base has size 4, and the slope has size 3, and it's exactly the situation here, the base and the slope. So you see, in this case, we cannot actually do this procedure, because if you cut down the 3 points from the slope, you get 3 points at the bottom, which is equal to the new base. So that doesn't work. And that was something similar to, yeah, you know, there was a somewhat similar reason why in the previous case we couldn't move the base up parallel to the slope. Now, what is the cardinality in this case? Well, you see again, so this exceptional situation happens when n probably has a special form. So here, how is n going to look like? Well, n, you can calculate. You have the base, which is s plus 1, and then you add them up all the way, and the last term is 2s. And when you plug numbers, you get 3s squared plus s over 2, which is the other triangular number omega of minus s. So in this case, you have this, if n is of this form, all the other partitions can be mapped to a partition of the opposite kind, except for this partition that cannot be mapped. So that's why this explains this this difference of 1 between these two numbers. So again, in the cases that so it's right here, when n doesn't equal omega of minus omega of minus m or omega of m, when n is not a triangular number, then we have a bijective correspondence. And in the cases that n is of this form, you have a bijective correspondence for all but one of the parts, which, so one of these partitions has one extra element than the other. Okay. Now, so let me say one more thing about it. So if you go back to what we were talking about, the partitions number. So remember that Pn was the number of partitions of n. We had this expression for its generating function. So sum of n greater or equal to 1 of Pn, Tn has an expression as a infinite product, as product for k greater or equal to 1 of 1 over 1 minus xk. That's how you can express Pn as the coefficient of Tn in this. It's not x here, it should be t. Sorry, it's tk. Okay. Now it turns out that using the previous result, you can actually figure out, well, what happens in this infinite product if I do a product of 1 minus tk. So in this case, you see each term has a sign. So if you when you're looking at the coefficient of t to some power, let's say 100, then that's going to be, if you expand it, is a summation for n, say, greater or equal to 0 of Pen minus Pon t to the n. So I'll leave this as an exercise for you to figure out, but it comes from the sign in front. And by the previous result, this actually equals 1 plus a summation over all m greater or equal to 1 of something like this, minus 1 to the power m minus 1 x t to the power omega m plus t to the power omega of minus m. Okay. Anyway, so that's this expression of this infinite product as a formal power series. Okay. All right, so that's all I wanted to say about this topic, this pentagonal numbers result. So let me move on now to talk about the topic that we started last time, Young tableaux. So I'll just call them tableaux. So here, as I mentioned before, you have some partition of a number. Let's say n equals 4, and so you have a partition which you can represent by a diagram. So there are many of them, and so that's the simplest. But in the you fill this this tableau with entries from 1 to n, such that each row and each column the entries are in increasing order. So here, if you have just one row, there's only one way. It's 1, 2, 3, 4. But let's say if I give you something like this, well, yeah, you can do 1, 3, 4. You can do a 2 here. If I give you something like this, you can do a 1, 2, 3, and a 4 here. Let's give you the same shape. And do a 1, 2, 4, and a 3 here. Here, let's say 1, 2, 4, and a 3. And they're actually there is a reason why I write them in this way. I'll mention you after I'm done. So there are 5 more. So this one is 1, 3, 4, and 2. Then we have this one here, which is a 1, 2, 3, and 4. And I'll give you 2 square ones. And 3 and 2, 4. And this one. 1, 2, and 3, 4. And the last one, the vertical one, it's clear, it's just 1, 2, 3, 4. So in this case, we have 10 Young tableaux for n equals 4. And it turns out the most amazing thing happens is that the number of tableaux with entries 1, 2, blah, 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 n equals the number of involutions in Sn. Maybe we didn't say what an involution is. An involution is a permutation for which the disjoint cycle decomposition consists only of fixed points and transposition. That can be written as a product of disjoint transpositions and fixed points. So I'll give you an example in a second. So here the I will write this permutation in a one-line or notation. So the first one is the identity 1, 2, 3, 4. That one has 4 fixed points, so we consider them as disjoint cycles. Then I can give you the next one, 2, 1, 3, 4. That's a product of the two transpositions 2, 1, and 3, 4, which are disjoint. The next one is 3, 2, 1, 4. So here, this is just the transposition 1, 3, and 2 and 4 are fixed points, and so on. So 4, 2, 3, 1. Here it's the transposition 1, 4, and then 1, 3, 2, 4, and so on. So 1, 4, 3, 2, 1, 2, 4, 3, 3, 4, 1, 2, 3, 4, 1, 2. Oh, no, this one I messed it up. This one is 2, 1, 4, 3, and 3, 4, 1, 2, and then 4, 3, 2, 1. So this, what I wrote here is taken from Don Knuth, Art of Computer Programming, Volume 3. And he presents it very well in that my presentation from here is taken from his book, from his wonderful book. And there's a quote there about this result, this theorem here, that so he says that this result is by no means obvious, and there is probably no simple way of proving it. So I'll give you a sketch of the idea of the proof, and then we can talk about the number of involutions in Sn. What can we say about the number of involutions of Sn? That's, by this theorem, it's the same as the number of tableaux with entries 1 to n. And then I will give you the hook length formula, which is a formula for the number of tableaux of a given shape in which the parts of the partition have a given size. So here, we're just counting all the tableaux. Okay, so let me give you the idea for this result. So the idea is based on what is called, now it's referred to as Rsk Correspondence. And R stands for Robinson. Studied this problem in connection with questions in graph theory, in group theory, 1938. S stands for Shenstedt. Studied this problem independently in combinatorial means in 1961. And K stands for Donald Knuth, who also investigated this problem in the 1970s. Okay. So before essentially the theorem that it gives a bijective correspondence between permutations here, permutations in Sn and order pairs PQ of the same shape with entries 1 to n. Okay, so you have this bijection between permutation in Sn and order pairs, and it has a. So I haven't described the bijection, but it has some remarkable properties. So let's say this is A, and B is that basically it associates to each permutation in Sn, it associates two of these two Young tableaux, order pair of the same shape in with entries in n. And the entry associated to the inverse, sigma minus 1, is the order pair QP. Okay, and so for that's a property of this correspondence. And what happens is that if you have an involution, so involution, you have that sigma equals sigma minus 1. So in that situation, the pair PQ is the same thing as the pair QP. So basically P and Q are the same. So this way, this correspondence gives you a, as sigma runs through all the involutions, whatever sigma is mapped to is going to run over all the tableaux of with n entries. Okay. So let me give you an idea about how this is done. So a crucial part of this procedure is about an inserting algorithm. So what's happening here? Say we have some young tableau. We have a young tableau. So let me give you an example of one. Again, this is taken from Knut's book. So let's say we have 1, 3, 5. Let me write it here. 1, 3, 5, 9, 12, 16. And then we have 2, 6, 10, 15, 4, 13, 14, 11, and 17. So let's say we have this tableau. Okay, and the only element that you don't see there is I think the element 8. So let's say we have an element 8, and we want to insert 8 into this tableau. Then what does this algorithm do? Well, you try to insert it in the first row, and basically 8 looks on the first row. You have 1, 3, 5, so 1. 8 sees 1, so it has to be to the right of 1. Then it sees 3. Well, 8 is bigger than 3, so it has to be to the right of 3. So the position of 8, the right position of 8 is where this 9 is. So that's where 8 goes first. So 8 essentially bumps 9 from this position. So I will write now what happens. 1, 3, 5, 8 has gone here. We have a 12 and we have a 16. So that's the first row. Okay. But now what does 9 do? Well, 9 has been bumped by 8. So 9 looks on the second row and does the same thing. You have 2, 6, 10. So now 9 will bump 10. Okay. So 2, 6, this is where 9 goes now, and then we have 15. Well, what does 10 do? Well, 10 looks at the next row, 4, 13, 14, and now 10 will bump 13, so it will be 4, 10, and 14. So 13, well, 13 looks, and the next row is 11, and on 11, 13 can just go at the end of the row and it causes no problem. So that's where it goes, and we have this new young tableau. Okay, so this is the procedure for inserting an element into a young tableau. Okay, and now the procedure, you see that the element 13 has been placed in a position that is a special position. It's so on this tableau, this position here, it has no entry to the right of it here, and it has no entry below it. That's where 13 has been placed. So usually these positions are called corners of the Young tableau. So the corners of the first Young tableau will be 16 here, 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 and here. 11 is not a corner, and the corners here will be 16, 15, 14, 13, and 17. So this procedure of inserting can be reversed. And you have a delete algorithm that if you start with a Young tableau and you give me a corner, can delete you basically you can run this insert algorithm, you can run it backwards. And so let's write it here and see how would that work. If let's say if we had 1, 3, 5, 8, which is the same one on the previous page, 12, 16. So in this situation, if we are told that that the position where 13 now used to be blank, and we want to go backwards to find out what was the tableau there, so you kind of go backwards like this, and you look, okay, where do we think 13 used to sit? Well, so you're gonna have the first 11 here, 17, and now we will build it up the tableau. Well, 13 was bumped down because it must have been bumped by that 10, so 13 must have sat there. And then we look at the 10 and we say, okay, where did 10 come from? Well, 10 must have come from by being bumped there by the 9. So you have a 2, 6, 10, and 15. And then we do the same thing with 9. And we get the previous tableau. Okay, so that's basically the procedure in reverse. Okay, so now, okay, quickly in 2 minutes, how does this procedure go? The Rsk correspondence. So you start with the permutation sigma. So let's just write in 1, 2. There's something more general in which you can start with a permutation of multisets and so on, but don't worry about it for now. We have something like this. So now from here, we are going to construct 2 tableaus, the P and the Q. And the way we do it, we start with the P, and we go in the, so we we start with the second row of the permutation. We go in the increasing order of the indices on the first row, and the entries here on the first row are gonna go in the Q, and the entry here are gonna go in the P. Okay. So let me see how that works. So how does it work? You take sigma 1 and you insert sigma 1 into a Young tableau, which is just one entry, and this one is going to be the entry 1. And then we repeatedly apply the insert algorithm on the left. And when we apply that, you know, we keep increasing making the tableau bigger and bigger. And so after we do that, then on the right in the Q, what we do is that we put the position QST, we assign the position I. So if here we inserted sigma I. So here we inserted sigma I in the position position ST. So S row and T column. Then in Q, in the position ST, we are going to put an I. Okay. So let me give you some example. Okay, let me give you a big example, and then we are gonna be done with this. So let me give you a big permutation. So let's say sigma is, I'll just write, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And here I have 6, 1, 7, 2, 5, 2, 5, 6, 8, 9, 3, 4. Okay. So here I will have the P, and here I will have the Q. So the P starts with a 6. So the first step, you get a 6. And the corresponding entry in the Q is a 1 above it. Then as we move to the right, the second entry in the, so the entries here go in the P, and this one's going in the Q. Second entry in the second row is 1. So by our algorithm, this becomes 1, 6. Okay. And Q changes, we have a 1, 2. So in that situation, we are going to put a 1 here and a 2 here. Now we've taken 6 and 1. The next one is 7. So that one goes, you have a 1 here, you have a 7 here, and we have a 6 below it. So we keep the same thing here as a 1 and a 2, and we put here the 3. The next entry is a 2. So now we start bumping things. So we have the 2 bumps the 7, and then 7 goes back in line here. So we have 6, 7. Now what happens here? In this situation, we keep the same shape, and in the position where we put the 7, we put the next entry, which is a 4. And now the next one, there's a 5 here. So we end up with 1. That one goes straight in the back of the line. Oh, that was nice. 6, 7. Same thing here. 1, 3, 5, 2, 4. Then the next one is an 8. So I can just put it here. There's an 8. And this one is a 6. And then okay, there's a 9. I can put the 9 here, and that is a 7. Okay. And what number comes next? There's a 3 that comes now. We have a 3 there. So the 3, we do bumping, it bumps the 5 from the first row. So it goes, make it a bit bigger. So it goes 1, 2, 3, 8, 9. And the 5 is bumped, and where does it go? 5 goes on the second row, and it bumps the 6, and the 6 goes at the end here, 6. So it gives us the same thing as here. And then you have a 2, 4, 9. No, it's a 2 and 4. So we have a 1, 3, 5, 6, 7. We have a 2, 4, and then this one is an 8. And the last one, you basically have a 4. So we have a 1. So the 4 bumps, where does it go? It bumps the 8, so it goes here. Now the 8 goes down, and the second line is 5, 7, so the 8 just goes here. And then the 6 goes here. So it's going to be the same thing as here, and with 1 at the end. So we have 1, 3, 5, 6, 7, 2, 4, You get a 9 at the end and 8. Okay. So this is the algorithm that gives you this these two order pairs PQ of tableaus. And we'll do some examples next time in which we apply this algorithm to involutions, and you will see in that case that P and Q are going to be equal, and that will give us the correspondence that we have here between these 10 Young tableaus here and these 10 involutions over here. Okay, so I'll stop here for this lecture.